Hello everyone, this is the video lecture for Calculus 3, section 14.6, gradient. So what is a gradient? Well, we have grad f, you say this like grad f, or just gradient of f, something like that, equals, here's your formula, in a vector, f sub x, f sub y, and then f sub z. Okay, so what's going on here is you basically have your derivatives, your partial derivatives, in respect to the element in which they're standing. This is like your x, y, and z point or on a vector. Or I guess in relation to the axes. Essentially, these are your slopes. This is a slope vector in a way. We've already seen this before on another problem. We were using A, B, and C for like the slope of a tangent plane or something kind of like that. This is your slope vector, essentially. There's another formula that they're going to want to talk about. This is the directional derivative. Directional derivative. And so let me show you what it looks like. Capital D, subscript U of F. And so, just before we keep going, just want to make sure and clear what we're doing here. A capital D, a subscript U, and then just a regular F beside it. And so this is equal to grad F at P dot U vector divided by magnitude of U vector. And you might be wondering, what is all that? So let me go ahead and fill in some pieces here. This guy right here is your gradient of f. You're plugging in your p. It's a point that they'd have to give you. And this is a unit vector. So notice that we have a vector and then times another vector. Well, that must then be a dot product. Okay. And just as an alternative version, you could also use grad f at p dot cosine theta sine theta. It kind of just depends. In this particular case, I'm saying, hey, we have an angle on the unit circle. So there you go. The directional derivative, essentially, it says how high, how much slope. I mean, this is all really just, again, slope. But in a particular, I can't spell it, particular direction. Okay, so like, this doesn't happen because it's a plane really. Let's say we have this right here, and we got north, east, south, and west. And so I'm saying, hey, along this pathway right here, how much slope do I have? Well, this is a plane, so you might have a constant, or you might even have 0. But what if you had like a hilltop, and you're sitting on the side of the hill here, and you're wanting to travel up towards the center there. But the thing is that north was not exactly there. It's not exactly north you're traveling, it's just a little to the side. And so you have to have that unit vector, I guess, in that direction. And if you're going up, you would get a positive. Let's say we're going this way, you would get a negative because you're going down. So, again, it's going to result, it's a dot product, right? So you're going to result in a number, in a scalar, and it'll tell you how much up and down you're going. But again, it's just a slope. So, 14.6.004. So I've got f of xy equal to x, y cubed minus x squared. They give me a point 1, 3, and they also say that theta is equal to pi over 3, and they want the directional derivative. So we got to do a little bit of math beforehand, like a little bit of calculus. So again, that's grad f at p dot, and then notice that we have a theta, so then this would definitely be the sine and cosine unit circle version that we'll be using. Okay, so what's my directional derivative? Again, it's a vector. All my derivatives are in terms of x. So again, here x, you would get a y cubed. This guy, the 2 comes down to x. Now your derivative in terms of y, and so then the 3 is going to come down, 3xy squared. There's nothing there, you leave it alone. I still have to plug in my p, 1 comma 3, and then I can see what these answers are going to be. That's, again, 60 degrees, so I should get a cosine that's smaller and a sine that's larger. Go ahead and plug in that p. So you got, again, this is an x and y, of course, right? So we got 3 cubed minus 2 times 1, and then we got 3 times 1 times 3 squared. That's a squared. You'll just have to trust me. Dot 1/2 square root 3 over 2. So doing the math here, we got 3 cubed is 27 minus 2 is 25. This guy right here, this is 3 cubed essentially, makes it 27. And I know it might have been a while since we done a dot product, but essentially you're multiplying those together, adding them up, and then there you go. So 25 times 1/2 plus 27 times square root 3 over 2. You know what's funny is that you actually are done. There's nothing else to talk here. I'm going to ask you, though, is it positive or negative? And you're going to say it's positive, so you're going up. Like, basically, if you're looking at it, this is all 3 dimensions, essentially. You're starting at this point here, right here, 1 comma 3. 1, 2, 3. So I don't know where you are height-wise, but we're sitting somewhere around there. And then we got unit circle. You're thinking there's like a little unit circle here, and you're going, that was 0, so you're going now 60 degrees this way, so you're trying to travel that way. And what is this shape here? I am not sure. I'm just going to make up something. Bloop, bloop, bloop. There you go. So you're actually right here, you're traveling this way, but apparently you're actually going up because you got a positive answer there. So maybe my hilltop there. There you go. You're going up it. Again, it's not easy to always see unless it's like a plain old hill, and I will talk about that when we get to those problems. So here we go. 14,6009. So I've got my f of x, y is equal to x over y. P is 6 comma 1, and they give me a unit. Well, they give me a vector. I don't want to always assume it's unit, though it is a unit vector here indeed. That is a unit vector. You can double check by doing the magnitude and all that stuff. And you would see that you got 1. So that's a unit vector. Anyways, you don't want to assume that. Sometimes they'll just do like 3 and 4 and good luck, figure it out. But this is a legitimate unit vector, so we can use that here in our directional derivative. And so, what's my derivative of this in terms of x? Is actually pretty easy. It's 1 over y. But notice whenever we're taking a derivative in terms of y, what if I were to rewrite this as x, y to the negative 1? Therefore, it's a negative. The negative comes down, leaves the x. And then now y to the negative 2, which is basically in the denominator. At 6 comma 1, still got to plug that in. Dot, and then we would have 3 over 5, 4 over 5. Let me go ahead and plug in those numbers there. And so 1 over 1 is a 1. Here we got a negative 6 over 1 is just negative 6. And then, of course, dot product 1 times 3/5. I guess it could be minus technically. There we go. So we got 3/5, and then we got negative 24/5. So in the end, I'm pretty sure negative 21/5. There you go. Notice that this is negative, so we're actually going down z-wise. Again, somewhere here on the xy plane. I don't know if we're up or down, doesn't matter. But in the end, we're going to be traveling downwards, like from some kind of slope. We're sloping downwards at that point, at this point, in this direction. Okay? Cool. Seems like we just got a whole lot of these problems. So here's another one. my f is equal to 7e to the x sine of y. P is 0 comma pi over 3. Kind of strange to see that radian stuff there. And v vector is equal to negative 3 comma 4. Notice this is not unit, so I need to find its magnitude real fast. Square root 3 squared plus 4 squared. I'm pretty sure it's a 5, a 3, 4, 5 triangle. All right, so grad f at p dot u, or I guess we can use the v technically here over magnitude of v. My derivative of this in terms of x simply should be the same thing. What's your derivative of e to the x is e to the x. But now your derivative in terms of y will turn that sine into a cosine at 0 comma pi over 3. And then dot, and then you can see basically it's going to be similar to the last problem where we're having that division by 5 stuff. Plugging in the zeros and all that stuff. When you plug in a 0 for your x, those are going to go to 1s. The 7 is retained. And then we got this pi over 3. So essentially we got 7 sine of pi over 3, 7 cosine of pi over 3. Dot my 3 over 5 and 4 over 5. Okay. We just did this as well at 60 degrees. Therefore, we have 7 square root 3 over 2. And this will be 7 over 2, essentially. Dot product. So we multiply them here. I don't think much cancels. So negative 21 square root of 3 over 10. And then these guys here, we got 28 over 10. Yeah, you should be just basically done. I mean, you can probably simplify a little bit, but it's whatever. Looks good enough. Okay. Yet another one. Apparently, I have a lot of these stored up here. It's an important topic. I mean, it's very important to do, but I got S's and T's in this particular case. So you could probably guess that those are not X's and Y's. And then notice my unit vector. It's not a unit, sorry. It's not a unit vector. It has a magnitude of something else. So magnitude of v, square root of 2 squared plus 1 squared is square root 5. If you're noticing something small, see the negative 1, and I don't even write it as negative, I know that 2 negatives will make a positive in the end. Therefore, it's not a really big deal. Okay, let's find my gradient. So I guess you could say grad g at p dot v over magnitude of v. Okay. The next problem actually is a little different, so that's good. And moving on, my derivative in terms of the s, I'm guessing that comes first, is just going to be square root t. In terms of t, again, you could think of this as like a half power, which is going to come down to the front. So half st to the negative 1/2. You can make that look a little bit more pretty, and I probably will in just a second. 2 over square root 5, negative 1 over square root of 5. We still have to plug in my p. I forgot to do that. So plugging in my s and my t here, I'm going to have square root of 9. I think it'll look just a tiny bit better. And then I got 1/2 3 times, and this is basically divide by the square root of 9. Notice that it has a negative, so it's got to be in the denominator. Okay. Dot product. Well, okay, hold on. We got a 3 right here. This is a 3 and the 3, and those are going to cancel. So I got a 3 times this stuff will make a 6 over square root 5. Technically a minus now because of my negative right there. 1/2, and this guy should make a 2 in the bottom. I guess what we could do is factor out the square root 5 stuff. And so you get 6 minus 1/2 is 11 over 2. That's what I wrote down. Some of these things it seems like, oh yeah, you just know it. I don't. I have to go and use a calculator. So like from here to there, It's a good thing to use calculator on stuff like that. So ultimately, should be like this. No need to rationalize or anything. But again, notice that it's positive. That means you're going up. Okay. Finally, something a little different, and by little I mean very little. I have an f is equal to 4y square root x. I have a p point at 4, 5, and they say find the max rate of change. Find the max rate of change and its direction vectors. And direction vectors. So what the heck are they meaning here? What is that? Well, when they say max rate, max slope, so I'm going to find my slope, which, as you probably have guessed, is grad f. My directional derivative is a slope, but that's in a specific direction. It's kind of like I'm trying to find the direction here, in a way. So let's not go there. I'm just finding my slope, my maximum slope. So first off, what are going to be my slopes? So grad f. In terms of x, again, that's a half. It's going to come to the front, makes that a 2. Hold on. 2y, and then that's going to move into the bottom as square root x down there. Again, it's 1/2 minus 1 is now negative half. In terms of y, it's actually much easier. Just square root x right there. Cool. So that's basically my slopes at any point. But now they give us a p. You probably ought to plug it in. And so we got essentially, what is that going to be? 8 over square root 5. No. I mixed them. I'm sorry. Hold on. It's 10 over 2. Yeah. And then 4 times the 2. So 10 over 2 is a 5. 4 times 2 is 8. So I got this guy right here. This is actually pretty important because they're wanting the max rate of change. Rate of change, you should see a slope. So what's the max slope? Well, it's basically going to be the magnitude of what I just found. Sorry, kind of rewrote it wrong. It's the magnitude of what I just found. So 5 squared plus 8 squared. That's 25 plus blah, 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 blah. It's square root 89. There you go. For speed's sake. Okay, so square root 89, that's your first answer. That's your maximum slope or whatever. And then they're going to want this, find the direction vector or something like that. Well, basically we had it at 5, 8. And so what we're going to be doing is dividing it by its magnitude to make it the unit, I suppose, that they're wanting. Well, that's basically your answer, part B. So that's A, that's part B. There you go. You should be able to type that in just as you see it into WebAssign. Pretty sure it'll accept it. Okay, this is actually going to be the last problem that I have. Not because they're not cool, but because this one's a nice big application-y problem. I think that this problem, before I get started, I'm telling you, it's a little bit tasking because it asks A through G. And so there's a lot of different parts. So we're going to get through it. It's not bad. It's just a little weird to kind of understand what they're asking for, okay? So I think the concept is really cool, though. So you're climbing up a hill. Okay, you're climbing a hill. I don't want to say up because that implies positive. But you're climbing a hill, and its shape, thankfully, looks like z equals 1600 minus 0.005x squared minus 0.01y squared. They say that we're standing at the point 60, 40, 15, 66. And they're also saying that the positive x-axis is east, and that the positive y-axis is north, just so that we understand. Basically here they're saying east and north, well, therefore west and south. Notice that this is in a 2D plane. This is my x's. This is my y's. But we're talking now z coming up out of that. So this, again, this is an x. This is a y. Okay. Before I keep going, I know they're going to start talking about slopes and stuff, so I just did my grad z real quick. The 1600 goes away. The 2 comes into the front, makes it a negative. There's a vector here. Negative 0.01x. And then right here, the 2 comes down. Negative 0.02y. Okay, awesome. Very good. Okay. I don't know how I'm going to use it yet, but here we go. Part A, it says, you want to walk south. Are you eventually going to ascend, or are you going to descend? Now, what are we talking about? How are we going to find this? Let's kind of do a concept. This original here, the shape, is basically a paraboloid that's upside down. I believe it's centered at 0, 0 as well. So definitely I'm not perfect about the scale, but it's basically like one big hill. And we were standing on some place of it. I'm not sure exactly where. They're saying 60-40, so somewhere over here probably. And we're wanting to walk south. We want to walk south. Now, we can't go through the hill. Are we going to be coming up, basically, so that we can come back down? Notice, kind of like a contour line to where I was. I'm going south, so I'm going to have to go up on the hill a little bit before I go down. Or is it that I'm already kind of on a side so that I would go down? I don't really know, and we're going to do the math to figure that out. So, this is my terribly temporary way of figuring it out. I don't want you to do this every time. I'm going to show you the proper way here in a minute, but let me do it my kind of weird way, okay? We're talking south here, so we're going to have a negative y value, I guess. I don't want to say y value, just a negative y. You're going along on your axes, you're going down. That's south down there. You're going down on the xy plane. And so I'm looking at my y's, and I'm going to basically say that my y's alone are negative. I know this is kind of weird, but notice that 2 negatives should end up being a positive in the end. And if you have a positive slope, you're supposed to ascend. Now that's there's your answer, but that is really strange how it works that way. What you're wanting to do actually is make a unit vector that makes sense for walk south. And so walking south is this way. I guess you can say 0, -1. And what I'm going to simply do is I'm going to dot product it with this stuff here, okay? So I would say I got this right here and here. I'm going to dot it with 0, -1. And again, I actually don't like this way at all now that I'm thinking about it. I did it at first and I thought, oh yeah, and then I started doing it the proper way and this makes more sense. Dot product and all that stuff. Well, we have an x and a y. I think that was like 60 and 40, something like that. Was that right? Was it 60 and 40? Yeah, 60. So this right here, this is a 60. This is a 40. So when you do your dot product, anything times 0, 0, and these times these guys multiply together, notice 2 negatives will again make a positive. So even without actually finding the number itself, because all this is times 1, this is my answer. It's definitely positive. Thus, I'm going to ascend. Cool. And part B, it's good to do this because it's saying by how much? By how much? And they ask it as in saying, like, what's your rate? And so essentially it's this guy right here, 0.2 times the 60. Whoa, I'm doing it wrong. It's not 60, it's 40. Right there, I said it was 40. Why did I say 60? Okay, well, it's a 40. Sorry, messed up a little bit there. 0.02 times the 40 should make a... hold on. Ooh, yeah, here we go, 0.08. It's kind of strange how I did it, but whatever. Okay, there we go. Next, next part C. It says, so we're doing it all over again. Walk northwest. So, Cartesian plane, we're talking this way. North, west. They're kind of going right in the middle there. So, walking northwest, what is that going to look like? Well, I'm going to make a unit vector. I'm going to say it's at a 45-degree angle because that's actually what they're trying to say. -1 for x, but +1 for y, divided by the magnitude of a square root 2. Notice that this is a unit vector. Very important there. And so I now dot product it. So I've got -0.01 times that 60, -0.02 times that 40, dot, and then I got this guy right here. So -1 over square root 2, +1 over square root 2. Awesome. Dot product, again, these two, those two, added up, etc. And I actually got -0.14142. Notice that this is negative, so you will be descending here. Okay, so that's your answer to part C. And then part D says, at what rate? And what they actually want in this particular case is positive 0.14. Why positive? It was a negative, right? So why a positive? Well, it's not because it's negative or positive. They want the absolute value. And it just so happened that we had it positive already, so we didn't have to do that absolute value on the last one. Kind of silly, I know. Again, that's why we're covering it, but it's just a very technical kind of problem. E, they say, what's the direction of the largest slope? Or the direction slope, where is it the largest? Honestly, it's just whenever you plug in those original points. This is very similar to what we had done with the last problem. We just plugged it in and said, well, there you go. So there's your answer. So that was easy. And then it says, okay, well, F, what is that rate? And so whenever you do your magnitude for that one, for all this, what's your magnitude? It actually comes out to be a 1. Isn't that kind of weird? It's a 1. G is the strangest question ever. Let me try to, I guess, put it in the language they're saying. I'm trying to remember what they're asking. They're saying something about, what's the angle with the horizontal at which your slope at the maximum is going? What angle? And that just is strange. Blah, 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 blah. It's going to just be the arctan, by the way. So arctan of 1, that number. Arctan of this number goes here, and it turns out that made it at 45 degrees. It's just strangely worded. That's why I wanted to cover it with you. I think the concept is really cool. I just wish that we did more applicable ones, I suppose. Okay, that's it. I'm done. Thank you very much. Have a great day.